Hello. Okay, I think you guys can hear me. Welcome to homework 13. Um, this time around, I'm not using the board. I just have the solutions in the slides. So I'm just going to go through them. They're pretty straightforward. And it's going to be a lot easier for your calculation. For those of you that have had trouble trying to see what I write on the board. So this last couple of homeworks and recitations, we're just going to do it this way. So I'm going to share right now. So that's what we have. So this is what we are working on. I believe you guys can see this. So make it bigger. So this is the first question here. Focus on concept question 04. The drawing shows a composite or composite slab consisting of 3 materials through which heat is conducted from left to right. So these materials, they have identical thickness, cross-sectional areas, but they are different materials, so they'll have different thermal conductivities. So they're trying to ask us which one has the highest thermal conductivity, followed by which. So it's easy to see from here that the temperature difference for this slab 1, or you see it's from 65 to 45. So that's 20 degrees delta T. Temperature change for slab 2 is 30 to 45. That's 15 degrees. And for 3 is 25. That's 5 degrees. So the same, you see, the same heat conducted, but the temperature change is different due to their thermal conductivity. So one, the temperature goes through, fast, like high. The other one, the temperature goes through 15. The third one, it goes through only by 5 degrees Celsius. So now let's see how thermal conductivity is related to temperature change. Is it a direct proportionality? So the higher the temperature change, the higher, or is it an inverse proportionality? The smaller the temperature change, the higher the temp. So this is what you look. So I'm going to bring out the equation here in the next slide. So this is the equation for thermal conductivity. Q is joules per second. Sometimes they put Q over T, so you know explicitly. D is the thickness of the slab, A is the area, and delta T. So thermal conductivity is inversely as delta T. So which means the more delta T you have, the smaller the K. So the one with the smallest delta T is 3, so that's going to have the highest K, followed by 2, followed by 1. So delta T for slab 3 is 5 degrees Celsius, 30 minus 25. Delta T for slab 2 is 45 minus 30, 15 degrees Celsius. That's the next highest one. And then the smallest one is 65 minus 45, which is 20 degrees Celsius delta T. So that'll give us the smallest K. That's why the answer is C. K3 is larger than K2, then followed by K1. Okay. Then the next question, focus on concept question 07 says, the wings of a soaring eagle are fully spread but not moving. So as the eagle glides through the air, it's also gaining altitude. So why is it gaining altitude? Because of the currents, the air currents. So the air currents are going upward or downwards. So those air currents moving through air particles through what we call convection. So those convection currents are what causes it. So the answer is B, not conduction and not radiation. And then chapter 13, problem 03 says a person's body is covered with 1.73 meters squared of wool clothing. So the thickness of the wool is 2.01 times 10 to the power minus 3 meters. The temperature at the outside surface of the wool is that. And the skin temperature is that. How much heat per second? So you're looking for Q over T, heat per second. Does the person lose due to conduction? So this is the formula you're going to use. I'm going to show you on the next slide how to do that. So we know what K is for wool is given. And we are given delta T. So 35.5 minus 7.54. That's going to be delta T, the change in temperature. L is given, the thickness of the wool, and then A is given. So we have everything we need to solve this problem. So Q over T, joules per second, that's what we're looking for, like power in watts. Ka delta T, the difference between 34.4 and 8.56, that's just going to give you that. Okay. So yeah, the values are a little different here, but it's the same problem. So I'm solving with this area 1.36, thickness of wool 1.19, 34.4 final temperature 8.56, the smaller temperature. So my temperature changes 34.4 minus 8.56, 25.84. So you just put that in here divided by the thickness, and then you get your answer in joules per second. Straightforward. The next one says one end of an iron poker is placed in a fire where the temperature is that, and the other end has that temperature. So we are given the radius and the length. So from the radius, we're going to calculate the area. Okay. Ignoring heat lost along the length of the poker, find the amount of heat conducted from one end of the poker to the other. So the area is going to be pi r squared, pi times the radius squared. So that's what you have here. The thermal conductivity is given to be 79 joules per second per meters per degree Celsius, times the area, pi times radius squared, that's what you have here, times the temperature change, which is given as 545 minus 27, times the time divided by the length. So that's going to give you the amount of heat. So this is not the amount of heat per second, just the amount of heat in joules. So there is difference between when you're asked to find the amount of heat per second, joules per second, and there is difference when you're asked to find just the amount of heat in joules. So now seconds will go out, T will be multiplied, and you are given the time through which the conduction took place. Okay, next problem 13, chapter 13, problem 21. So we are the amount of radiant power produced by the sun is approximately that. So we are given the radiant power, which is Q divided by time. Assuming the sun to be a perfect black body, so E equals 1 for perfect black body emissivity. Sphere with radius of these, find its surface temperature in Kelvin. So we're looking for T in Kelvin. Okay, so we'll have this Stefan Boltzmann equation, sorry. So we have the Boltzmann constant right here. So which is 5.67 times 10 to the negative 8. So we just solve for T from this equation, which is 4th root of Q over T over E over sigma over A. But Q over T is given to you as the power already. We put that there. So you just put E to be 1, sigma to be Boltzmann's constant. Then 4 pi r squared for your A, because it's a sphere. That's the surface area for a sphere. And then you just plug and chug. Next one, a person is standing outdoors in the shade where the temperature is 30 degrees Celsius. What is the radiant energy absorbed per second by his head when it is covered with hair? The surface area of the hair assumed to be flat is that, and its emissivity is that. Then what would be the radiant energy absorbed if he were bald and the emissivity of the head is that? So it's just plug and chug. Same problem you have here. So we're just going to do the amount of energy absorbed per second. So from the same Stefan Boltzmann, so we're going to see this E sigma T to the 4A, just do that. E sigma T to the 4A. So you are given the temperature in degrees Celsius. So the trick to solving this problem is your temperatures in this case are going to be in Kelvin. So you can see for 30, we add 273 to 30 to get the temperature to be 303 before we raise it to power 4. And the same for this guy. So everything is the same. The only thing that's changing is the emissivity. Is that okay? The emissivity is the only thing that's changing. Everything is the same. That's how you get the two different areas. Two different answers here. Sorry. Okay. Next, suppose the skin temperature of a naked person is that. When the person is standing inside a room whose temperature is that, the skin area of the individual is 1.4 meters square. Hello, close the door. Thank you. Assuming the emissivity is 0.747, it's okay, you can come. Come on, shut the door. Close the door, come on. Come. Okay, sorry, my daughter is distracting me. Come on, come sit down here. Come, let them see your face. Come on, Miriam. You want to say hi? Say hi. You want to learn some physics?
No.
Okay, good. No. So assuming the emissivity is that, find the net loss of radiant power from the body. That's the A part of the problem. The B part said determine the number of food calories of energy that is lost in 2.1 hours due to the net loss rate obtained in part A. Okay. So first of all, to get the radiant power loss, that's Q over T. We use this equation as usual. The T goes down to give us power Q over T. And we convert our temperature to Kelvin as usual. Okay. And then, so this is the radiant power lost by the body. Then we'll do the same for the room. So the only difference is the temperature change. So the temperature for the body is different. The temperature for the body was 35.3. We're going to add 273 to that. And then the temperature for the room was 28.1. We're going to add 273 plus that. So Every other thing is the same. So we get the power for the body absorbed, the radiant power gained by the room and the radiant power lost by the body. And then we take the difference for the net loss of radiant power. So the net energy lost by the body is just power times time to get energy, because energy over time is power, and we just got the power already. Okay, so we'll get that energy, but they want it in calories. So that's why they're converting 1 calorie is 4186 joules. And then you get that answer in calories. Okay, next question. Focus on concept question 01. Say all but one of the following statement is true. Which one is not true? A mass in grams equal to the molecular mass in atomic mass units of a pure substance contains the same number of molecules no matter what the substance is. True. Avogadro's number. B, 1 mole of a pure substance contains the same number of molecules. True. 10 grams of a pure substance contains twice as many molecules as 5 grams of that substance. True. 10 grams of a pure substance contains the same number of molecules no matter what the substance is. No, not 10 grams, okay? It's only 1 mole that has the same. Avogadro's number of molecules of a pure substance and 1 mole of the substance have the same mass. No, so the one that's not correct is D. All the others are correct. Is that okay? If the speed of every atom in a monoatomic ideal gas were doubled, the Kelvin temperature of the gas will be multiplied by a factor of 4. How did you get 4? This is how the speed, the root mean square speed, V squared, is related to temperature. So if I put V to be 2V and I square 2V, is going to give me 4. So whatever happens on the other side has to be multiplied by 4 on the temperature side. That's how you get 4 for that one. Question 07, focus on concept, says the atomic mass of a nitrogen atom is 14 we call it atomic units, while that of oxygen atom is 16. 3 diatomic gases have the same temperature: nitrogen, oxygen, and nitric oxide. Rank these gases in ascending order, smallest to first, according to the values of their translational root mean square speeds. So the lighter one is going to have the highest speed, basically. So oxygen, O2 is 16 times 2, which is 32, okay, in ascending order. So let's see NO. NO is 14. You see that now? 14 plus 16, that's NO. So that's lesser than 32. So that's going to have more translational RMS speed. And N2 is just 14 plus 14, which is less than 14 plus 16. So N2 has higher, followed by NO, followed by O2. Next question. Hemoglobin has a molecular mass of that. Find the mass in kilograms of 182 molecules of hemoglobin. So I can get the number of, this is the mass of hemoglobin, which is the molar mass. Is that okay? So that divided by Avogadro's number, which is the number of molecules per mole, will give me the grams. Is that okay? So now I have this in grams. Is that okay? So this times 182 molecules divided by 6.02 times 10 to the power 23 moles, as in molecules per mole. So mole cancel mole, molecule cancel molecule. All I have is grams. I convert grams to kilograms by dividing by 1000, and I get the answer I want. So this 9.5 E minus 20 means 9.5 times 10 to the power minus 20 kilograms, okay? I mean 1.95 times 10 to the power minus 20 kilograms, sorry. Okay, next problem says, chapter 14, problem 02. Manufacturers of headache remedies routinely claim that their own brands are more potent pain relievers than the competing brands. Their way of making the comparison is to compare the number of molecules in the standard dosage. Tylenol uses 325 milligrams of acetaminophen, which is this guy. So we're going to add mass of carbon, mass of 9 hydrogen, 8 carbon, 1 nitrogen, 2 oxygen to get the molecular mass of this guy. While Advil uses 2 times 10 to the power 2 milligrams of ibuprofen, so we're going to do 13 times molecular mass of carbon, hydrogen, molecular mass times 18 plus oxygen, molecular mass times 2 to get the molecular mass of ibuprofen. So find the number of molecules of pain reliever in the standard doses of both A and B, Advil and Tylenol. So let's see how that works. So first of all, let's get the molecular mass of Tylenol. 8 times carbon has 12.011 U plus hydrogen is just 1.00794 U times 9. Nitrogen is 14 points. So we're going to add all these masses and oxygen times 2, we get this. We do the same thing for Advil, 13 times carbon mass plus 18 times hydrogen mass plus 2 times oxygen mass, atomic mass unit. So we now have the molecular mass of Tylenol and molecular mass of Advil. So the next thing to do now is number of molecules is number of moles times, Avogadro's number. And number of moles is mass over molecular mass. Okay, so the mass is given in the problem, which is 325 milligrams. So you convert that to grams divided by gram per mole, because these are mostly chemistry, working gram per mole. Sorry, let me shut this door because of the noise. Okay. Times Avogadro's number, and that just gives us the number of molecules. So the same thing for Advil, we just put the mass of Advil given in the problem, which is given to be 2 times 10 to the 2 milligrams. So multiply that times 10 to the negative 3, you get 10 to the negative 1 grams, and then divided by the molar mass of Advil we just got, times the Avogadro's number. That gives us the number of molecules that are present there, and that's the 2 answers you have. Next is chapter 14, problem 07. It says a runner weighs 618 and 71% of this weight is water. How many moles of water are in the runner's body? So first of all, let's get the weight of the percentage weight that's water. So number of moles is mass over mass per mole. So the mass is the weight divided by G, which is 71% of the weight given. 0.71 times weight divided by G, that's what you have here, over mass per mole, that's the number of moles. So mass per mole is given. Is that okay? Is that okay for water? So I'm going to convert that to, kilograms. So after getting that, number of moles is this over mass per mole. I've gotten mass per mole in kilograms because this is in SI units. So that's why I'm converting to kilograms, because I have newtons on top, which is kilogram meters per second squared. So when I solve this, put 600 newtons, 71% of 600 newtons is the weight divided by G, 9.8. That's my mass. Mass per mole is this for H2O, for water. And then you get your number of moles. So the number of water molecules in the runner's body, that's the second part of the problem. Number of molecules is number of moles times Avogadro's constant. So we just get this. Next is a 0.012 meter cube container is initially evacuated. Then 5.27 grams of water is placed in the container, and after some time, all of the water evaporates. If the temperature of the water vapor is 423 Kelvin, what is its pressure? So this is just using PV equals nRT, but N is mass over molar mass. That's all you need to do. So mass over molar mass for water is your N, number of moles, then times R is a constant, 8.31, and then times the temperature given, 423 Kelvin divided by the volume. Every other thing is given to you to get the pressure. It's the ideal gas equation. PV equals nRT, and you replace N by M over mass per mole. Okay. Next one, chapter 14, problem 23 says a primitive diving bell consists of a cylindrical tank with one end open and one end closed. The tank is lowered into a freshwater lake, open end downward. Water rises into the tank, compressing the trapped air, whose temperature remains constant during this descent. The tank is brought to a halt when the distance between the surface of the water in the tank and the surface of the lake is 46.5 meters. Atmospheric pressure at the surface of the lake is that, atmospheric pressure 1.013 times 1.5. Find the fraction of the tank's volume that is filled with air. So let's see what's going to happen here. So volume, for H over volume of tank, so we're just taking the ratio. Is that okay? It's volume of H over volume of surface. Is that okay? So which is proportional to pressure at surface over pressure at H. Okay? So what we're saying here is P1V1, so you know that equals P2V2, right? Is that okay? So the volume and the pressures are inversely proportional using that. Okay? So but P at surface plus rho GH is P at the height at the bottom. So rho GH is an added pressure. So this is all I need to put here. So I get the pressure at the surface, atmospheric pressure plus rho GH. I get that. So I put that here. So VH over V tank is the ratio of the volume, the fraction of the tank's volume that is filled with air, equals P surface over pH. We know P surface is atmospheric pressure over the pressure at the depth at H, and that solves the problem basically. Okay. Next says a bubble located 0.22 meters beneath the surface, that's a problem 27, chapter 14. In a glass of beer rises to the top. The air pressure at the top is that atmospheric pressure. Assume that the density of beer is the same as that of fresh water. If the temperature and number of moles of CO2 remain constant as the bubble rises, find the ratio of its volume at the top to that at the bottom. So the same thing, V1 over V2 is P2 over V1, inverse proportionality, but P2 is P1 plus rho GH. So we'll just do P1 over P1 is 1, rho GH over P1 stays there, and then that just gives us V1 over V2, 1 plus rho GH over P1. And that gives us exactly like the previous problem. Just give us that. Okay. So rho is the density of water, 1000 kilogram per meter cube. The H is given 0.22, G is just 9.8. And P1 is atmospheric pressure at the top. Next is chapter 14, problem 35, go. Suppose a tank contains 709 meter cube of neon at an absolute pressure of 1.01, that's atmospheric pressure. The temperature is changed from that to that. What is the increase in internal energy of neon? So increase in internal energy is final minus initial difference. So when you take the difference, one internal energy is nRT final, that's PV, basically, pressure times volume, minus 3 over 2 nRT, initial. So it's just 3 over 2 nRT final minus T initial. And we know how to find nR because P initial V equals nRT initial. So from here we can find nR because we don't know what the number of moles is, but we can find nR because they are both constant, they are the same. So it's going to be P initial V over Ti. So I used it for nR in this equation up here, and then that's like change in internal energy. Okay. The next says chapter 14, problem 36. 2 moles of an ideal gas are placed in a container whose volume is that. The absolute pressure of the gas is 6.5 10⁻⁵ Pascal. What is the average translational kinetic energy? So we're going to use this formula now to get there. But the capital N here is small n times Avogadro's constant. So okay, that's number of molecules. So number of moles times Avogadro's number gives us number of molecules. So this is just the only thing you substitute in this equation. And from here, you can now solve for the average kinetic energy. So that we're not using 3 kT because we don't know the temperature, we're using 3 PV over 2N. So P is the pressure, V is the volume, N is number of moles, which is given 2 moles, times Avogadro's number, which is given here. Okay, so 2 times 2 moles times Avogadro's number is 100. 3 times pressure times volume is given, and that gives you your answer directly. And the last problem says, chapter 14, problem 46, a tube has a length of 0.017 meters and a cross-sectional area of 5.3 times 10 to the minus 4 meters squared. So the tube is filled with a solution of sucrose in water. The diffusion constant of sucrose is given by that. So we're just going to use what we call the Fick's law for time. So solve Fick's law for time, and you get mass times length over d. Is that okay? Which is the diffusion constant times area times delta C. Is that okay? Good. And we'll have delta C to be the concentration difference, 3.5 times 10⁻³ minus 3. So we'll just put all that in here, and we just get the answer directly. So it's quicker this way to see the solutions right in front of you and able to use the values of your problem to solve what you have here. The values might be different, but the procedure and the equations are the same. So I'm going to stop sharing right now, and I'll see you guys in the next homework. Thank you.